In this video, we will deal with the oxidizing nature of halogens. Basically, we will be comparing the oxidizing power of various halogens, whether a particular halogen will be acting as a strong oxidizing agent or a weak oxidizing agent. And then we will do some questions on the basis of the concept that we will be learning in this lecture. Now, we have to deal with the oxidizing nature of halogens. So, we must understand what does oxidizing nature mean. Oxidizing nature means it should increase the oxidation state of the species with which it is undergoing reaction and get itself reduced. That means it should reduce the oxidation state of itself. So we are talking about halogens, and halogens generally exist as X2 molecule. So during the oxidation of other species, halogen should get reduced. That means we have the oxidation state 0 for diatomic species, and it should get negative in order to get reduced. Now, during the conversion of X2 to X minus, there would be some energy associated with the conversion of X2 to X minus. Now, a compound would be a better oxidizing agent if the energy associated with the conversion of X2 to X minus is released. The greater the energy released for the conversion of X2 to X minus, the better the oxidizing agent that halogen would be. And there would be several energies that would be associated with the conversion of X2 to X minus that we are going to discuss here in detail. Now we will start with X2 and we will have to go to X minus aqueous. So first of all, we will have to break the bond between X2, and for this we will be requiring bond dissociation energy. Next we'll have to add an electron to X gas, and this would associate electron affinity, which would the energy released. And next we'll have to hydrate that particular anion to form X minus aqueous, and here we'll have hydration energy, which will again be a released energy. So we have three different kinds of energy for the conversion of X2 to X minus. The first one being bond dissociation energy, which would be the required energy. Next would be electron gain enthalpy, electron affinity basically, which would be a released energy. Next, hydration energy, which would be a released energy again. So we'll have to see the order of various halogens for these three particular energies, and then we will see that in which case the released energy will be greater in order to set the correct order of oxidizing nature of various halogens. So if you look at the bond dissociation energy, then the order comes like this. Now you must wonder that why F2 being smaller in size, the bond length of F2 is smaller, and despite this fact it has got a less bond dissociation energy. We have learned that bond dissociation energy is inversely proportional to bond length. But in case of fluorine, what happens that we know that despite having a lesser bond length, it has got lone pairs of electron, and since the bond length is less, so the electronic repulsion increases significantly, and therefore the bond dissociation energy decreases. Next we have electron affinity, and for this we have the order as shown here, and in this also we have fluorine, we have after chlorine, and the reason for this is fluorine having a smaller size, whenever new electrons are added, then despite of the attractive force between nucleus and the electron, there is also a repulsive force between the electrons adjacent to it, and so the energy released is slightly less than chlorine. And next we have hydration energy. We have studied that hydration energy is inversely proportional to size, so we know that F minus having the least size will have the greatest hydration energy, which is a released energy. And on the basis of these three energies, we have come to a conclusion that the energy released is greatest in case of fluorine, followed by chlorine, followed by bromine, and followed by iodine. The order has been shown here. Oxidizing nature order is as follows, and reducing nature, the order of reducing nature would be opposite to that of oxidizing nature. Now whenever we talk of oxidizing nature, we think in terms of F2, diatomic species, because whenever this species will oxidize other species, it will get reduced to a negative oxidation state, And whenever we think of reducing nature, we think of F minus, because whenever it would reduce the other species involved, it would get oxidize itself into a zero oxidation state of diatomic species. Now we have the reasoning here. Due to low bond dissociation energy and high hydration energy, fluorine is most oxidizing among all halogens. Now we will do in this question, we have to select the pair of species which can't exist together. Now whenever we have two species, and suppose species 1 and species 2. Now whenever these two species one will be oxidizing in nature and another will be reducing in nature, suppose oxidizing agent and reducing agent. When these two species will react with each other, then we will have a redox reaction, and so in that case we will say that these two species cannot exist together. Now we have Pb plus 4 here. We have learned that in group 16th, in sixth period, in group 13th, 14th and 15th, we have inert pair effect, and that means that the lower oxidation state is stable, and the elements that comes in the sixth period in group 13th, 14th and 15th is Tl, Pb and bismuth. And for these three elements, the lower oxidation is stable. For example, plus 1 for Tl, thallium, plus 2 for bismuth, and plus 2 for lead, and plus 3 for bismuth. Now in the first question we have Pb plus 4 and I minus. We see that Pb plus 2 is a stable oxidation state, so Pb plus 4 must get reduced to Pb plus 2. That means it should get itself reduced, that means it is the oxidizing agent, and I minus should get itself oxidized to I2, that means it is a reducing agent. So we have an oxidizing agent and we have a reducing agent, that means it cannot exist together. Similar the explanation for the B part and for the C part. For the D part also we have Cl2. Now we have learned that Cl2 is a good oxidizing agent, it comes here, and I2 and I minus is a good reducing agent. So these two again are a good oxidizing agent and a good reducing agent, so it cannot exist together. And similar is the explanation for the E part and the F part. Now we have this question, we have to arrange the following in correct order of stability. Now in this question we have the similar concept here. In PbF4, the oxidation state of Pb is plus 4 and that of F is minus 1. Now we know that Pb is stable in plus 2 oxidation state, and in every compound here Pb is in plus 4, Pb is in plus 4, Pb is in plus 4. Now Pb wants to be in plus 2 oxidation state, and in the compound we have Pb is in plus 4 oxidation state. Now if the anion involved is a good oxidizing agent, then in that case the plus 4 oxidation state of Pb would be stable. So we have learned that fluorine is a very good oxidizing agent, so it will help to keep Pb in plus 4 oxidation state, and so PbF4 would be the most stable among these. And similarly, Cl being a slightly less better oxidation state than fluorine, but better oxidation state than bromine and iodine, so PbCl4 would be relatively greater stable than PbBr4 and PbI4. Similarly, we can order the stability of these compounds on the basis of this particular reasoning that has been explained. So the order would be like this, and similar explanation can be given for the next question, and the order would be like this, because fluorine is a strong oxidizing agent and Tl here is in plus 3 state. Tl wants to be in plus 1 state, so to keep it in plus 3 state we need a strong oxidizing agent, which is a fluorine. Now for the GeCl2, here we see that this Cl is common, okay, and we have learned that as we go down the group, then lower oxidation state is most stable. So as we go down the group, germanium is first in the group, followed by tin, followed by lead. So as we go down the group, we have plus 2 state and plus 2 state. So lower oxidation state should be stable. So Pb in +2 stable will be much more happy than Sn in +2 state, and Sn in +2 state would be much happy than Ge in +2 state. So the stability order would be like this. And in the next question we have similar question. In this we have in the +4 state, Sn +4 state and lead +4 state. We have learned that as we go down the group, lower oxidation state is more stable, Pb being the lowest in the group among Ge, Sn and Pb. So it will not be happy at all in the +4 oxidation state. So it would be least stable. Compared to Ge and Sn, Ge being upper in the group will be much more happier than Sn in the higher oxidation state. So the stability order would be like this. And here we have the explanation of the question, and this is a fact that we must remember. So let us end this lecture at this point of time. I hope you have understood what would be the correct order of the oxidizing nature of various halogens, what should be the reasoning behind it, and we have also learned the application of that particular order in deciding the stability of various compounds. We have seen that a particular compound should be stable in higher oxidation state if it is associated with a halogen which has a higher oxidizing nature, and a particular compound will be happier in a lower oxidation state if it is associated with a halogen which has a poor oxidizing nature. So I think these concepts are quite clear, and we will be able to apply these concepts in solving the questions quite confidently. So in next lecture we will deal with another important topic, that is pseudohalides.